316 million. Just imagine, for a second, a giant cosmic measuring tape stretching out into the utter dark of space. You'd literally need to spool it out for a mind-boggling 316 million units before you even hit our target for today.
And those units aren't miles, and they're definitely not kilometers. We're talking about 316 million light years away. That is the immense, almost unimaginable gulf we're crossing today to look at a true behemoth of the deep cosmos.
Welcome to this explainer. Today, we're dissecting one of the most extreme, frankly fascinating objects in the entire universe. It's called NGC 4874, also known as Coma A. This thing is an absolute monster of a galaxy, and by looking closely at the data, we're going to figure out exactly how it works.
Okay, let's dive into our flight plan. First, we'll meet the cosmic giant. Second, the cosmic distance ladder. Third, a swarm of star clusters. Fourth, the surviving X-ray corona. And finally, a dynamic cosmic dance.
Section 1. Meet the cosmic giant.
So let's set the stage. NGC 4874 is a supergiant elliptical CD galaxy. It's this incredibly bright anchor located right in the Coma Berenices constellation. Now, it was actually first spotted by the legendary astronomer William Herschel way back on April 11th, 1785. But, Herschel could really only see a fuzzy smudge through his telescope. Today, we know so much more.
When we look at the optical data, NGC 4874 is sitting right at the absolute heart of the Coma cluster. And it isn't just floating there, it entirely dominates the space. It resides at the very peak of the cluster's gravitational potential, literally anchoring hundreds of other galaxies all around it. It really is the reigning monarch of this patch of space.
Section 2. The cosmic distance ladder.
Now, you might be wondering, how do astronomers actually know this galaxy is 316 million light-years away? Well, it comes down to one of the most clever techniques in astrophysics, surface brightness fluctuations, or SBFs. Think of it kind of like looking at a digital photograph. If you take a picture of a huge crowd up close, you can easily see individual faces, right? The image looks highly textured or grainy from pixel to pixel. But if you take a photo of that exact same crowd from a mile away, all those faces just blend together into a smooth, uniform blur. Galaxies work exactly the same way. By measuring this pixel-to-pixel variance in the infrared K-band using the Keck telescope, researchers Liu and Graham were able to precisely calculate the massive distance to NGC 4874. And here's why that is absolutely crucial. By measuring the distance to this specific galaxy, astronomers were able to help pin down the Hubble constant, which is literally the rate at which our entire universe is expanding. The SBF data from Coma A yielded a Hubble constant of 71 kilometers per second per megaparsec. So this single, distant galaxy is actually helping us measure the scale of the entire universe. How cool is that?
Section 3. A swarm of star clusters.
Now that we know exactly where it is, let's zoom in a layer deeper. We're moving from the whole galaxy down to thousands of tiny ancient objects buzzing around it like a massive swarm of bees. All these tiny points in the photometric data are globular clusters. They're ancient, incredibly compact, gravitationally bound systems of stars that actually formed in the very early universe. Because NGC 4874 is so incredibly massive, it holds on to an enormously rich system of these clusters. To really understand them, researchers like Hartman and her team used something called spectral energy distribution, or SED fitting. Because they had data from 10 different Hubble Space Telescope filters, covering wavelength all the way from the blue to the red, they didn't have to just guess. They could accurately weigh these distant star clusters. They found that these clusters have mass-to-light ratios of around 2 to 4. That means they're actually slightly heavier for the amount of light they emit compared to the typical clusters we find in our own Milky Way. It's just a fascinating testament to the totally unique environment of this giant galaxy.
Section 4. The surviving X-ray corona.
But visible light only tells us half the story here. The Coma cluster is a harsh, incredibly hot laboratory of X-ray physics. When we view the data in X-rays, we see that NGC 4874 possesses this dense, surviving corona of hot gas. But what's truly spectacular is the radio data mixed in. NGC 4874 is firing off these massive wide-angle tail radio jets. And notice this, those dramatic twisting jets only become visible outside the protective envelope of the X-ray corona. Inside the corona, the jets are shielded, but the second they punch through into the wider intracluster medium, they just get swept back by the galaxy's sheer velocity plowing through space.
Now this gets genuinely mysterious when you compare NGC 4874 to its next-door neighbor, the giant NGC 4889. NGC 4889 shows these distinct central X-ray cavities, basically hollowed-out bubbles from an active outburst that's gently heating the gas. But NGC 4874, despite having those massive radio jets we just talked about, deep Chandra X-ray observations show absolutely no central cavities. None. It's a profound puzzle. How can active galactic nucleus feedback behave so incredibly differently in two giant galaxies sitting right next to each other in the exact same cluster environment?
And make no mistake, the engine driving NGC 4874 is terrifyingly powerful. Based on the data, the supermassive black hole at the core of this galaxy packs a mass of 1.7 billion times that of our Sun. A 1.7 billion solar mass engine fueling those massive radio jets, yet somehow leaving its surrounding X-ray corona perfectly intact. Incredible.
Section 5. A dynamic cosmic dance.
So, what is the ultimate fate of our cosmic giant? To answer that, we have to look at the kinematic data, the actual physical movement of the stars at the very, very edges of the galaxy. When researchers measured the halos of NGC 4874, they found a flat velocity dispersion profile of about 283 kilometers per second. Now, why does that matter to us? Well, if the stars at the extreme outer edges were speeding up, it would mean they were being torn away, just free-floating out into the larger cluster. But a flat profile proves that these outer stars are still firmly gravitationally bound to NGC 4874. The giant is holding itself together.
But, it won't last forever. The Coma cluster is unrelaxed. It's currently undergoing a massive merger. The data paints a pretty dramatic picture. NGC 4874 and its neighbor, NGC 4889, are locked in a slow, incredibly destructive gravitational collision. As they fall toward each other, they are tidally stripping each other's outer halos, creating this vast, elongated sea of intracluster stars.
Which leaves us with this final, awe-inspiring thought. We've seen the 1.7 billion solar mass black hole, we've looked at the shielding X-ray corona, and the thousands of ancient star clusters. But eventually, millions of years from now, NGC 4874 and NGC 4889 are going to collide completely. What happens to the cluster, to the black holes, and to the surrounding space when two absolute cosmic behemoths finally become one? It's a question that keeps astronomers looking up, and I really hope it keeps you curious too. Thanks for joining me on this explainer, and keep exploring.